afternoon everyone. Welcome back to the session on fundamentals of computers. In the morning class we were discussing about different kinds of job schedulings and what are the different types of jobs we can have. One was CPU bound and the other was input output bound. After that we stopped at this slide where I was trying to explain you about the uniprogramming system. So if you keenly observe at this point, what is it that is happening in a uniprogramming system? In a uniprogramming system, we have the main memory. In the main memory, the operating system and the user job both are taking its schedules, and then after that you have the CPU. The CPU is connected, or it's talking with the user job, whatever job that needs to be done. So the main thing you have to see is only one job is processed by the system at a time, and all the system resources are exclusively available for the job until it is completed. So in uniprogramming, as we discussed, all the resources that are there that are available by the computer, they are only exclusively used by that one user job, and once that user job is completed, only then there is another task that can be processed. Only one job is processed by the system at a time, and all the system resources are exclusively available for the job until it is completed. So that is what is a uniprogramming system, and you should be able to draw this diagram, or you should be able to explain this diagram if someone asks you, or if you should be when you are asked by someone. Okay. So next we have multiprogramming. I was telling you about different tasks, right? When we have three, four tasks like T1, T2, T3, T4, we had these examples, or otherwise we had different examples like Microsoft Word, PowerPoint, PDF, browser, music application. When you are using all of them, how is the CPU managing all of them with the help of RAM? That is what we were seeing previously. We had such examples also. So now if you see this is your secondary disk storage. What do you mean by secondary disk storage? It is connected with your primary memory in the secondary unit, and this secondary disk storage is your hard disk or whatever disk drives that you have for storage. All the data that you process is stored in this, and it is used for your data. And now how is it connected? As we have already seen in the previous block diagrams, that your secondary disk storage is directly connected to the main memory, and this main memory is in turn connected to the CPU. That is what we have seen in the block diagram previously also. Now the same diagram is here, but it is giving you even more details about the different processes that are happening inside your multiprogramming system. Okay. Now if you see this, the main memory is the most crucial part for any programming concept. Whether you take uniprogramming, whether you take multiprogramming, multiprocessing, multitasking, multithreading, whatever it is, all the operations have their changes only in the main memory concept. If you understand the changes that are happening in the main memory, then you will be able to easily differentiate between the different programming concepts we have. So in this, what was the thing that was happening in uniprogramming? We only had one user job, and that user job was performed by the main memory, and there are no other jobs that are being performed. Once this user job is completed, only then another task is assigned to that main memory, and it performs that. Whereas in multiprogramming, in the morning we discussed, there will be several programs that are doing their work concurrently. That is what we were mainly focusing in the morning class. So it appears as if they are all working at the same time, but as they are working at a very fast speed in nanoseconds, picoseconds of 10 power minus 9 or 10 power minus 12, it appears as if they are all working at the same speed, but it is not the case. So if you see the main memory for multiprogramming, your main memory definitely, or your RAM, it definitely takes a little portion for its operating system programs or for the functioning of the operating system. Other than that, it has enough memory storage for the for the other tasks to perform its operations or programs. So at this point we were discussing an example of 4 different programs: opening of a Word file, PDF, music folder and a music application and a browser folder or a browser application. Over here you can just see three of them. In this example, just consider A is the job for the Word file, B is the job for your browser, and C is the job for your music application or music player, whatever it is. So in such a case, what is happening? Your main memory has operating system, a little portion of it, to perform the other operations that are available as tasks, and then we have job A, that is Word file, job B, that is your browser, and job C, that is your music application, music player. Now job A is Word file, right? So when I double click on the job A, when I double click on the Word file, it is assigned a task in the main memory, and that is in turn talking with the CPU initially. As of now, don't consider this arrow, but don't see this arrow, but you just consider the arrow is migrated over there. And over here, what is happening? Just don't consider this arrow for a while, and consider the CPU is connected to the job A. At job A, we have a Microsoft Word application that is clicked by the user. When it is clicked, the CPU in turn processes the application and it opens that Microsoft Word file that is required for us. At that point, inside the Microsoft Word, we wanted to open a existing file. So what we do in the functions of the Microsoft Word, we go to the file and we click on existing file. When you click on the existing file, it has to fetch for that file in the secondary storage, because all the data for our files is stored in your hard disk, that is your secondary disk storage. In this secondary disk storage, the job A, that is the Word file, it goes and searches in the secondary storage. At that point, your CPU is idle. That is what we were talking about previously. When the CPU is idle, in multi-programming, the CPU is assigned to job B. Job B is the other job, that is your opening of a browser, that is opening of your browser in the main memory. The main memory is processing all the tasks that need to be done. Now job A, job B, job C. Job A went for, that is your Word file, it went to fetch the data in your secondary storage. Then we have job B. Job B is now assigned the CPU. Job B gets access to the CPU and it starts to open or reload a page that was already previously opened. When it is doing this its task, the CPU is not idle. That is what you have to see. In the case of multi-programming, what happened? When the job A is still going to just fetch the existing file, there was no other job that was present in the main memory. That is the reason the CPU was idle. So if we are able to assign CPU the remaining that are leftover tasks when the CPU is idle, then we will be able to get more efficient access or more efficiency, we will be able to get it. So at this point, job B is accessing the CPU and it's reloading a web page, or it is just opening a web page, a web browser, whatever is the task that you would like to assign. And then at that point, when the browser is opening and it's reloading the page, job C is your music player application that you have already clicked on to listen to the music. At that point, still the job C is waiting for the CPU access so that it will open the music player and it will play the required song for the user. Now, like this, there might be multiple jobs. This is just a basic diagram for you to understand how multi-programming works. We will see in the later programming concepts where how multi-programming is still, what are the disadvantages we have with multi-programming and what are the different concepts we have come up with to overcome these faults that we have in multi-programming. The problem with uni-programming operating system is it is only able to perform one job at a time, and even though there are other processes waiting for the task, they are not able to complete, they are not able to get the access to the CPU until the first job that was assigned to this CPU is completed. Until it executes all the process of that task, only then other processes, if they are in the line, they will be able to access it. That is why we came up with a concept where whatever jobs are waiting in the line. Whenever job A or job B, if they are going for an input output operation or for search fetching of the data from the secondary storage, the remaining jobs that is next in the queue, that will be assigned the CPU and that will be working with their process. Now, what is the first job? It is opening a Word file, and in that we are opening the existing Word file. When we are opening the existing Word file, it has a requirement with the secondary storage. So, it went to the secondary storage, it is collecting whatever data it wants. In the meanwhile, when the CPU is idle, job B is assigned. Job B is a opening of a browser, and while opening of the browser and when you are trying to connect to the internet, this does not require any other input, any output operation or input operation, or it does not require fetching data from the secondary storage. Suppose that is the task for us. Then the browser will open for us and the job B is done and it will come out of that line. At this point, if job A isn't allowing job B to do its work, where it doesn't have any other thing to do, only at like 2 seconds work. Job A has like 20 seconds work, job B has 2 seconds work. Job B has to wait for those 20 seconds to complete its 2 seconds work. That is the reason we are providing the other processes which are in the queue when the CPU is idle, so that those processes will be completed, as well as the CPU power or the CPU efficiency of the CPU will increase. That is the reason. And next, we have process states in multi-programming. This is a very important concept that you have to understand in multi-programming, because whatever operations that are happening in this main memory, they are happening in order to get connected to the CPU, get the access to the CPU, get their work done and complete its tasks. That is what they wanted. So, there are so many tasks being in the queue, and also they are trying to get the access of the CPU. So, for such scenarios, it is not an easy task to develop an algorithm or a program which will manage all of this. If you see this scenario, there is a new job that is ready, and that job is ready to get executed. The job is allocated to the CPU for execution, then it is running. Running means the job processing, it is processing the job, and the job processing is completed. In case like the job A, where it is requiring secondary storage access, the same way if this job also requires some access, then it won't complete the job. Instead, it will go and the job must wait for the input output operation to be completed. If the input output unit or the secondary storage is free, then it will directly go and it will get its input output completed, and it will again wait for its turn. Once it is completed, if there are any processes in between, it will wait for its turn, otherwise it will go, it will complete its running state and it will complete the job processing. The job processing is completed. Okay, just a minute. So, we are here, right? I would like to show you that with the, okay. Now, what was that was happening? We had job, and this job is wait a minute. We have something called the job, this job Okay, this is what we were previously looking at. This is the diagram that we are trying to understand. So this state is called the CPU. Over here it is CPU, and this will be your main memory. Okay, because in your main memory is where, suppose this is your main memory, let's suppose. Okay, and it has output. Just a minute. It has input, and in the main memory this is your operating system, right? And we have several other tasks that are waiting: P1, P2, P3, P4, this will be P5. This will be P5, and this main memory HDD, hard disk. Let's suppose this is your secondary memory. This is your secondary memory. Okay, now this is how it is all connected, and this is again connected to your CPU. This is your input out, like this is your normal mechanism of your computer. Now this thing and this thing are same, but this is only a even more clear picture of what this is. Generally what is happening, whatever tasks we are having, it is listed out in your main memory, and whenever there is the CPU is idle, each task is going and performing its operations with the CPU, right? So so what is happening when P1 is fetching for an input output operation? Let's go back to this scenario. This and this are same. I just drew that because you should understand both, like this is what is happening here, the same thing. Now we have a job. What is the job? P1 is our job. Now where is it going? Where is it going into the ready state? In the main memory, when it's entered, when the P1 job, it is entered into the main memory, it means it is ready to get performed. If it gets access to the CPU, it will complete its task and it will come out of the line. Okay, so that is what always happens in the processors. They are always ready to get into the CPU, complete its process, come out of the task. That is how they all try to P like. So we have how many processors? Suppose P1, P2, P3, P4, P5. We have all the 5 processors over here. These processors are always in a very much active state and they are always ready to get into the CPU, acquire the resource of the CPU, get its process done and come out of the loop. Now in the previous example we were only talking about P1 in the multi-programming example. Here in the multi-programming example over here, what were we talking about? We were only talking about if job A is going to the input output operation or it's going to access the secondary storage, then job B is getting access to the CPU and job B completes its task. That way we are improving the efficiency is what we were discussing. But even over here we have one problem, that is what we will be going to discuss in this diagram. That is, now let us assume like the same way P1 is going to the secondary memory to access some data that is stored on the secondary memory. Now P2 is assigned, at this point P2 is assigned the CPU, P2 is assigned the CPU and P2 starts performing its operation. Let us suppose P2 is a PowerPoint and PowerPoint is also having the same task just like your Word. P1 is your Word, suppose Word doc, okay. P1 is your Word doc and P2 is your PPT, PowerPoint, okay. Now P1, what is it doing when it's opened? The user again wants the Word document to open an existing file that is already saved in the secondary storage. Then what will happen? P1 will go to the CPU first, it will open the Word document, and when the user asks assigns the task of opening an existing document, P1 says CPU, I have another task with secondary memory where I have to retrieve the data. I will go and come back. In the meanwhile, what will the CPU do? It will have the second task P2 assigned to the CPU. At this point, when P2 entered into CPU, P2 is having PPT application to be opened. When it opens the application, the user again clicks on the file and he tries to open an existing file that is already there. Like just like the Word file that he or she created before, the PPT also is already existing, just like the PPT we have here, okay. If the user wants to open this existing PPT, he or she will again have to contact this secondary storage. Now here is where this diagram is really helpful for us in the understanding. Now job is P1, right? Initially we had P1 is the job. P1 went in, it's ready to get executed in the main memory over here, and then it's running. While it's running, it felt that it required the secondary storage data. So what it did, it went down and it is checking for the blocked state. This is a blocked state, okay. Now it checks for the blocked state. If in this state, if there is some other operation that is accessing this secondary drive, it has to wait over there and it cannot access the secondary memory directly, as there is some other process that is using the secondary memory. But in our case, P1 is the first process that started its job and it is directly ready and it went for running. When it's running, it wanted the access of secondary memory or this hard disk. Then it went down, it checked in the block state, there is nothing, there is no other process that is using the secondary memory. So it gets access to its data, whatever it is, it collects the data and it goes to the ready state again. It is ready with all the data and it is ready for process again. What is the process here? It went to the secondary memory and it checked that there is no other process using the second memory. So it went there, accessed its file and it's ready to show the user all the data that is there inside that Word document. So it's ready. Once it goes again to the running state, it will show all the data to the user and it completes its process. Now in this process where it went down and it was trying to fetch the data in the secondary memory, the CPU is idle, so the RAM, the second process that is there in the RAM, that is main memory, it is assigned to the CPU. When by the time this P1 process is here, P1 process accessing the hard disk. At this point, P2 went to the CPU, P2 is ready here, now P2 is ready here, first this went and then second it went into the ready, it is ready in the ready state, it goes to the running state, P1 and then P2 goes into the running state. At P2 running state, again the user wanted to open an existing PPT this time. So at this point, when P2 tries to go and access the HDD, it is in blocked state. The reason is the P2 process is blocked. It enters into this blocked state and waits until P1 completes its fetching of data from the hard disk. Once P1 completes its fetching from the hard disk and it goes to the ready state, at that point P2 is released from the block state and it gets access to the hard disk again. When will it happen? When P1 completes when P1 completes accessing hard disk. Okay, accessing hard disk. At this point, the P2 process, it is again changed from the block state to an active state, and it will be able to access the hard disk. In this process, these both P1 and P2 started from the ready state, it went to the running state, and both of them went down for the input output operations or fetching of the data. At that point, again the CPU is being idle. See over here, it's starting from the RAM, that is main memory. These two processes one by one they are going, and once these both are coming down, at that point again the CPU is idle, it doesn't have any other process. At that point, P3, which is a browser this time, it will be assigned from the ready state to the running state. It will complete its process and it goes. Even suppose if the browser also has some data to be retrieved, or it requires some input output function, then even the P3 process again comes into this position. If the input output device or whatever the hard disk device it wants, they are being used by some other process, then the P3 will also be in the block state. Once the other process is completed using whatever P3 wanted, the P3 state process, it comes from the block state out to the ready state. So this time P3 will also come here, and from the ready state again these things happen until and unless they require the required resources and the process needs to be completed. Until then the same loop the same loop follows. This is how the operations happen in your computer. Okay, and why is this all required? Like previously in this we were seeing about multiprogramming, and what do you understand in the multiprogramming over here? We are able to see job A, if it is working with the secondary storage, job B is assigned CPU, and if job B also requires the access to the secondary storage, that is why we came here. But you might ask me, or you might get a doubt like, why is the second process going into the block state instead of directly accessing the hard disk? The hard disk has so many files, and both the files are different, right? In the example we considered, Word is a different file, PPT is a different file, but still why is it that the hard disk is not being accessed when one more process is using the hard disk? The reason is, this is always this kind of an operation is always used, and it is always make sure to apply this kind of an operation, because suppose there are multiple users using the same file. For instance, suppose this Word file is there, right? If this Word file is being used by multiple people on the same operating system, then what will happen? The user 1, the P1 task is of user 1, P2 task is of user 2, but they both are trying to write to the same file at the same time, which would create so many issues with the data, with the writing of the data, and it actually spoils the integrity of the data. That is the reason we are putting all the process whatever they are in the block state when some other process is using either the input, output, or secondary storage. So this is about the process states in operating system. And then what are the requirements for multiprogramming operating system? We have to understand that. The requirements for multiprogramming operating system are large memory, memory protection, job status preservation, proper job mix, CPU and input output jobs, CPU schedule. We all understood now what do you mean by multi-programming systems. In multi-programming systems, we know that we require large memory, memory protection. Memory protection is very much required because whatever the processes are happening, they all need to be happened one after the other, and also even if if there is no protection to the data that is available in the multi-programming systems, the reliability and the accuracy of the systems wouldn't be there. So that is the reason we need to have memory protection. And then we have job status preservation. If you don't preserve the status of the jobs, what will happen? Over here we are using multiple processes, right? If you don't preserve the status of the Word document which went for accessing the hard disk space, then again the process, when it goes to the ready state, it has to start from the starting. It has to again restart the Word document and again ask the user for the input. Again the user will click on the existing file to open a previous file which is there in the hard disk. The P1 process will again go to the hard disk to fetch it. If the job state isn't preserved here, what will happen? Again it goes, when it goes to the ready state, it will be again new. So it will be in a loop all the time, and there wouldn't be a complete process that is happening if it comes out of the loop. Only those processes which are going in this line will be able to complete it. Otherwise, if it comes out of the loop or to a side lane where it has to access the input, output or secondary units, if the job state isn't preserved, then when it goes back to the ready state, the CPU again has to start from the starting for that job, because you don't have any details related to that task P1. So that is the reason. Okay. And then what is the next thing we have? Proper job mix, CPU and input output jobs. Proper job mix is in the sense, if the processes are not scheduled, or if they are not properly queued in one after the other, and if they are not properly aligned, then there would be efficiency in the CPU, right? So that is the reason we have to have proper job mixing. And then CPU scheduling. CPU scheduling is nothing but, CPU scheduling is always, you can just link the CPU scheduling with your idle time of the CPU. The better your CPU scheduling algorithm is, the better efficient and the more number of processes can be handled at the same time by the CPU. Okay. And then we have the process control block, PCB. PCB is used to preserve the job status of each loaded process in a multi-programming system. We will see this PCB in the next class, where we will start about the remaining concepts of multi-processing and multitasking. Okay. So that's all for today. Thank you.